I guess we will start now. It's 11 on the dot. So hi everyone, thank you so much for joining our WISA seminar today. So for those of you who don't know me, my name is Roxy Fournier. I am a postdoctoral fellow here at the University of Waterloo, and I work with a professor named Dr. Richard Hewson. And we do physiology research on astronauts. And so my background is heavily focused more on the health side and understanding the biological and physiological effects of spaceflight on the human body, and got to meet John a couple years ago now, I guess, when I first moved to Waterloo. And so, yeah, we connected, and there's a lot to learn on the human-computer interface side. And so I was really excited to be part of this event that John put together. And we're very, very fortunate today to have WISA's director here, Dr. Suzanne Kearns. And so I'm going to just give a brief introduction of her, and then she will give us a little brief intro about WISA. So Dr. Kearns is an aviation professor with over 2 decades of experience. So she's made significant contributions to aviation training, human factors, and sustainability. She earned an airplane and helicopter pilot license at the age of 17, which is super impressive, and began her academic career as a professor at the age of 24. Also extremely impressive. She has earned numerous accolades, including national and international awards, with her research and aviation leadership. And she's also the author and co-author of 6 influential books and peer-reviewed research articles. So in 2021, she founded the Waterloo Institute for Sustainable Aeronautics, WISA, and is leading research and education. It is a leading research and educational center dedicated to advancing sustainable aviation research, technologies, and education. So with that, I'll pass it over to Dr. Kearns.
Thank you so much, Roxy, and thank you to John for all of your work. Can I share my screen?
I think so, yeah.
Now we can.
All right, I can see it behind your head, so I can tell that it's working. So thank you so much for the opportunity to be here today and to join some distinguished colleagues. I think this is going to be a really exciting event. So I'm going to just take a few minutes and tell you a little bit about what WISA is and our mission. So when you think about WISA, so when we think of the term sustainability, the most important thing I think to kick off is the idea of what does the word sustainability mean? When many people hear the word sustainability, they think of greening or the environmental applications, and that's absolutely an essential part of sustainability, but it's not really the definition of sustainability. That sustainability really means long-term viability. It means the ability to meet the needs of today without sacrificing our ability to meet future generations' needs. So WISA, the core of WISA is sustainability. And we, as a research institute, we were founded during the pandemic. We're only about 2.5 years old, so we're kind of the new kids on campus, sort of the new organization on the block. And our mission, as Roxy mentioned, is to become a world-leading hub for sustainable aeronautical research, technology, and education. And as I mentioned, all of our work is sort of structured around these 3 pillars of sustainability. And really, when WISA was founded, it was founded because we were asking ourselves, what are the biggest threats facing the future viability of air transportation? And you can define those as a shortage of people, so not enough talent to sustain operations, growing emissions and environmental impacts of the sector, and rapid evolution of new technologies, which poses both challenges and opportunities to the viability of our sector. So interestingly, these challenges align with social, environmental, and economic sustainability. And when you think of sustainability in terms of these 3 pillars, you can recognize how it touches almost every academic discipline on campus. So I'll tell you a little bit about each of the pillars and some of the research areas that we consider to be in scope within each pillar. So again, social sustainability, this is the area actually that's closest to my personal area of interest and expertise, which is in the training and human factors realm. So social sustainability, we work with colleagues across campus who are looking at aspects of how do we create a viable, competent, and sustainable, safe workforce for the future of aviation. So this includes everything from human factors research to flight physiology. We look at aspects of machine learning to better understand how skill development happens, and that references also educational technology, so using the best tools to help people achieve competence. We look at equity, diversity, and inclusion because aviation's not very good at that yet, and we've got a lot of work to do, as currently only about 5% of pilots are women, less than 1% are people of color, and certainly not a representation of other equity-deserving groups as well. And we also want to make sure that aviation is a catalyst to help support society in the long term, to keep providing the access to mobility. So that links into things like sustainable tourism, smart cities, and healthy communities. And just as a quick story for those of our American colleagues, Canada being a massive country geographically, many of our northern and remote communities are only accessible by air for large stretches of the year. They're called fly-in communities, and all food and medicine and supplies are only accessible by small aircraft, which we call bush planes. So from a social sustainability perspective, aviation is also a catalyst to support those communities. Under environmental sustainability, the aviation industry has harmonized behind a target of net zero emissions by 2050. To achieve that goal, there's not one single solution. We need to mobilize all of these multiple solutions at the same time. So we're looking at things like sustainable aviation fuels, flight optimization, more direct flight paths, new technologies, looking at the integration of electric aviation and hydrogen propulsion. How can we reduce emissions, not just in the aircraft when they're flying, but in all of those airport-based operations that are happening on the ground as well. And just trying to integrate sustainability into the operating practices of every aviation company. And lastly, under economic sustainability, in full transparency, this is kind of the catch-all where we put all of the different research activities that are necessary that maybe don't fall into the social or environmental categories. So we would have things like our drone-based research, automation, artificial intelligence, and cybersecurity, basically anything that poses either an opportunity or a threat to the long-term viability of the sector. We know that that would directly impact the economic success of our industries. So one of the reasons that makes Waterloo a really special place for WISA and why we're really proud to be here is because Waterloo hosts Canada's largest undergraduate pilot training program. So we take in about 150 new student pilots into the first year of our program every single year, which creates a community of more than 300 across the four-year degree. These students come to Waterloo and they earn their pilot licenses while they're earning their four-year degree. So that makes it a really, really unique environment for all of your researchers to access pilots in training, so at all different levels of training. And when you visit the simulator later, it's a really great piece of research infrastructure because it allows us to use it as a tool using our wonderful pilot participants. So even though WISA is only about 2.5 years old, we have grown from about 30 faculty members to over 150. We have engaged almost 130 different businesses and organizations and fostered many new collaborations. Over 100 new intellectual properties, so new IP, have been produced since we launched. And in February of last year, we had announced a Fed of Ontario investment of $9.2 million, which we used to fund 38 research projects across the whole stretch of social, environmental, and economic sustainability. So that project ended in March, just a few months ago. And since we launched that, researchers have applied for an additional $30 million of funding. So it's really beginning to be a movement that we're really excited about. And I think that's reflected by the talent and everything that we're going to hear more of today. So thank you so much on behalf of WISA for coming together for this event. And I'm excited to learn more from all of you. Thank you.
Thank you so much, Suzanne. We appreciate that introduction. And I think it's a really good kind of primer to what we're going to be discussing today. And so we have three really awesome speakers that are going to be talking to you today over the course of an hour and a half. And then we also have for our in-person attendees a little demo for you at the WISA Sim Lab. That'll be one floor down in this in the environmental EV1 building here. So So our first speaker will be John. Were there any other housekeeping rules that you wanted to cover before we start?
Just for the people online, I try to keep your microphone off, and then if your camera off as well while we are presenting. I think those are the most important ones.
Yeah, and in terms of questions, so we'll have 3 back-to-back speakers, and then we do have some time set at the end for Q&A. We have about 20 minutes for Q&A. So do you want to do questions after each talk, or do you want them to reserve?
All at the end.
So yeah, so reserve your questions for the Q&A period that'll be happening after all the speakers have gone. All right?
For the people online, you can just write down the question, and then Roxy will be looking at how to cluster them and bring them the 50-20 minutes that we will have towards the end of the session today for answering.
Sounds great. Okay, so I'll introduce our first speaker, which is Dr. John Muniz. He's a game designer and interface technologist specializing in leveraging physiological signals to optimize user experiences in interactive systems. His research currently focuses on assistive interactive technologies using human-robot interaction, human-centered design, and virtual reality. John's currently an adjunct professor at the University of Waterloo in systems design and engineering department, and leads research in the physiological computing area. So Dr. Muniz has developed an array of software tools and design frameworks that seamlessly integrate playful activities and physiological signals into interactive systems, such as social robots and virtual simulations. So those who are in the audience here right now, you'll get to play with some of those tools that John has been working on later today. All right, so with that, I'll pass it over to John.
Great, thank you. Can you see my screen now? For the audience?
Yes.
Looks good. Okay, nice. It's great.
Just set it up to make sure we have it on in this room as well.
Nice. Now you can see it.
Yeah.
So thank you all for coming, and thank you again, Chad, Dr. Pope, Roxy, and Suzanne for helping us to organize this event and bring in our particular view for this technology. We are going to be here discussing around elements of physiological monitoring or physiological sensing. Overall, I will say there's also a growing body of literature calling physiological computing to many of the technologies we use for these. And I'm going to try to introduce the topic to you. So a lot of things that Chad and Dr. Pope will be bringing here will be familiar for some of you that are not familiar with this topic. So as I mentioned before, physiological computing is probably one of the terms that you will start finding here and there in the literature. And what this area of research really is this unique blending between conventional interfaces that we have and the ones that we conventionally use to interact and exchange information with psychophysiological monitoring system. In this particular case, we are talking about body sensors that can be attached to participants, or sensors that can be unobtrusively used to collect body information, physiological information. There's plenty of uses of this particular technology. You probably have seen in the past research being conducted in the collecting body or collecting physiological signals while somebody is interacting with any kind of system. That's the first use is user research. But this technology can be also used for biofeedback, so feeding back the signals so participants can see their own physiological signals in real time and be able to learn how to regulate that. Clinical psychologists tend to use that a lot. Today, we're also going to be talking about a very interesting concept called biocybernetic adaptation, which was pioneered back in the 80s and 90s in NASA Langley, which refers to the intelligent adaptation, allowing the machines to learn from the body signals in real time and create adaptations on the fly. So for the ones that are not familiar with physiological signals, we have a whole amalgam of body signals and metrics that can be collected, ranging from the most popular ones like electroencephalography, which records activity, brain activity, electrical activity of the brain. Electrocardiography records electrical activity from the heart. Electromyography, these are all electrophysiological metrics. EMG records from the muscles. Electrodermal activity records sweating activities from your sweat glands, and so on and so on. And you actually will be surprised with the complete list of physiological phenomena that can be recorded using these signals. But again, coming back to what's the type of phenomenon that we are trying to register here in the physiological or in the biomedical space, is called physiological signals or biosignals. And these signals may come from very different backgrounds or may come from very different sources. And there's multiple ways of categorizing these signals. Here I found one that is interesting, which talks about categories related to whether the signal is a permanent signal, for instance, electrocardiography, or if it is an induced signal, so a signal that requires an external element to be able to appear or show up. In this case, the electroplethysmogram, for instance, is one that requires a stimuli from the outside. Categorizations also can be based on how dynamic versus more quasi-static nature of the signal. Like, for instance, the body temperature doesn't really change much throughout the day versus the heart rate, which may have different changes. The one that I like the most is origin. So depending on the kind of physical phenomenon that we are recording, if it is electric, magnetic, mechanic, optic, acoustic, or chemical, we may have also particular signals depending on the phenomenon that we are trying to record. This is not an extensive list. Nevertheless, it's a pretty comprehensive list of the amount of signals that you will be able to find in the literature. And as you can see, acronyms are all over the place because we scientists love acronyms because that helps us to reduce the amount of words that we need to use in our conventional speech. We have electrophysiological signals. We have signals coming from optical sensors. We have signals coming from mechanical sensors. And again, this is a non-extensive list, but still allow us to identify that depending on the type of physiological phenomenon that you're trying to record, there's always a sensor, there's always a mechanism, always an instrument that will allow us to record those signals in real time. So in the field of physiological computing, we have multiple ways of using the signals. This is what I call the physiological computing continuum. We normally have a very popular way of using body signals or recording signals from participants when they are interacting with systems, and this is for user research. In the field of user experience or game user research, this is called biometrics. And you basically record the signals to explore the behavior of the participants while interacting with the system in a post hoc manner. So right after you're done with your experiment. Back in the 60s, 70s, clinical psychologists brought the concept of biofeedback. And the main point with this is feeding back the signals or the biosignals in real time and allowing participants to watch their signals and learn how to regulate, or in this case, self-regulate themselves by increasing or decreasing certain signals in real time. So breathing and many other techniques that can be used to control your body responses, which, by the way, is a skill that you need to master. It's not that easy for you just to connect sensors and think that you're going to regulate yourself just by breathing or concentrating. It requires mastering to be able to do that. So multiple sessions, normally multiple repetitions. Then researchers in the field of human-computer interaction started using the signals more as a control input in systems, so allowing people, for instance, with certain disabilities to be able to interact with conventional interfaces. So those kind of signals are used a lot for assisted devices and interactive assisting technologies such as brain-computer interfaces or to work with prosthetic devices. We will be briefly, and I think Dr. Pope and Chad would be mentioning some examples on how to use what is called biocybernetic adaptation or intelligent adaptation using biosignals as a way of allowing the machine to be more intelligent and to somehow provide these capabilities to learn on our body responses, on our physiological signals in real time, and be able to create more personalized systems. As you probably can see here, that requires a more active use of the physiological signals as opposed to a more passive one, which we conventionally use in user research. So we are here to briefly talk about the opportunities of physiological computing in aviation training. And this is not something that has been only happening recently. Actually, the aspect of physiological monitoring in the field of human factors, in particular for aviation, has been around for many decades. So there's nothing really new in that sense. What is new is how interestingly wearable, accessible and affordable the technologies are becoming, and the scripts and the technologies we use now to process the signals are becoming more and more popular among researchers. So we have seen a race of several studies focus on physiological monitoring tools for aviation training. I would say mostly focus on these four states or four areas of research, which also may be called psychophysiological states. First is mental workload. Second one is situation awareness. The third one is stress management, and the fourth one is fatigue. So considering those particular states, these are also some of the signals that have been most popularly used in aviation training to record body responses and try to, again, infer things such as stress or mental workload. I categorize some of those in groups such as cardiorespiratory. So we have a lot of the respiration information, heart rate variability, ECG, photoplethysmography. Those are signals that are commonly used because the heart is and measures of the heart and our cardiorespiratory functions can be very informative about our cognitive load and how we conventionally our brain works. Our heart and brain are connected is normally widely used to explore the dynamics of cognitive processing. We also have more direct measurements of the brain, neurophysiological measurements. In this particular case, EEG and fNIRS are probably the most widely used techniques to record neurophysiological signals. EEG stands for electroencephalography, fNIRS, functional near infrared spectroscopy. We also have measurements of electrodermal activity, which are very good to explore arousal and sympathetic activation. In this case, skin conductance levels and galvanic skin responses. And we normally use electrodes to record those on our hands, palms, and phalanges. Eye tracking, another very popular metric to explore features such as gaze fixation and pupil dilation, to explore mental workload. And I would say more recently we have seen more and more articles looking into kinematic metrics, especially inertial measurement units that are nowadays embedded on almost every device that we have, such as phones, smartwatches, wristbands. They all have inertial measurement units, and also facial expressions by using cameras or facial electromyography. So you can take a closer look over those articles that are really summarizing the papers that are or the signals that are most widely used for aviation training in terms of physiological monitoring. Now, normally when it comes to moving from just recording data to actually transform the data into something that we can use in research, that requires a pre-processing and processing stages. So we start with something like raw data. Imagine we have an electroencephalography, 16 channels. The raw data may look like this. But then you need to transform that into something that has certain meaning in the context of aviation training. So we normally transform the raw data into frequency bands, which are called oscillatory rhythms. Then we have alpha, beta, delta, theta, gamma, and many others. Those signals are, or those particular features are somehow helping us to explain mental states or psychophysiological states that we're trying to look. But still, by themselves, sometimes we need to combine, or we need to come out with different metrics to be able to get towards psychophysiological states that we want to explore in our research. So, for instance, back in 90s, at NASA, they created the engagement index, which is basically an index of beta, alpha, and theta, and combines those three oscillatory rhythms into something that is called the engagement index. So overall, between raw data and something that is actually usable or can be usable in this particular field, we may have to do this transformation of signals, which requires processing, pre-processing, cleaning, and feature extraction stages in order to collect that data. Now, once we have our particular features and we believe we want to explain, or we would like to use that to explain certain phenomenon, we also have some challenges related to what is called the psychophysiological relationships. So we are trying to explain a psychological state by using physiological signals, but it turns out that it is not a straightforward one-to-one relationship. So for every psychological state we have, normally we may have multiple physiological signals that will be affected by changes on those. And the same thing may happen with the physiological signals. One physiological signal might be affected by a particular change in your psychological state. So this is called psychophysiological, it was defined in the by John Cacioppo, an extraordinary psychophysiologist, back in the 2007, and defined these relationships. And the classic example of this is, imagine you were really stressed out about something that is happening because you are having some meetings and you're having a presentation in front of your mentors of NASA. So what tends to happen is you have increases, for instance, in your skin conductance level, or you may have changes in your heart rate variability, or you may have a negative valence related to your facial expressions and how they change because of your stress levels. So same thing may happen with any other psychophysiological state, and how those may affect the physiological signals is something that we normally study in the field of psychophysiology. Fortunately, nowadays, we have plenty of very interesting signal processing tools that can be used to facilitate the integration of this fantastic technology into our research. So this is, again, non-extensive list of open source, some of them, Python, MATLAB, C, C++, C# libraries that already exist with methods for you to learn how to process the physiological signals. Indeed, I had the opportunity to conduct a survey with about 12 software tools with 13 experts in these fields. And then most of the issues and main challenges that they have were related to software compatibility. So allowing multiple hardware tools to be able to work across different manufacturers. Limited options for data cleaning, processing, and interpretation, and as well as the data synchronization. So collecting multimodal physiological signals and being able to synchronize all of them as a way to conduct causality analysis is one of the probably most challenging tasks that we have nowadays in the field of psychophysiology. And in aviation training is not as different as it is as other related fields. The Waterloo Institute of Sustainable Aeronautics, we're trying to put together something that we call Compass, which is a database that will use multimodal physiological signals. The C stands for comprehensive, so basically looking into various aspects of pilot training and physiological monitoring. Operational would be, or will highlight the real world application of the system. Will be multimodal. We will try to collect signals from the brain, from our sweating glands, eye tracking, and kinematic information. Aviation is the type of content that we are providing to this. We will use the WISA simulator that the ones that are here in person would be able to see to basically collect this data while we have pilots under training or experienced pilots running some of these scenarios. And we will have an integrated database that hopefully researchers will be able to use once we are done concatenating all the data and putting it in a comprehensive database. So that's all that we will leave the questions towards the end. Thank you for attending this first talk.
Thank you, John. Yeah, so again, for those who may have just joined, if you have questions, please use the chat function of Teams here. Put your questions in the chat, or for those who are here in person, just keep them for the end. We have a Q&A period coming up. So thanks again, John. And then our next speaker we have is Dr. Alan Pope. So I'll just give a brief little introduction and then pass it over to him. So Dr. Alan Pope is a pioneering engineer-psychologist at NASA. And he studies how cockpit design affects crew performance. He's well known for his research on pilot vigilance, also known as hazardous awareness states, and biocybernetic adaptation, so technology adapting to humans. So Dr. Pope retired from civil service in 2016, but he's currently serving as a distinguished research associate at NASA's Langley Research Center, conducting research with brain-computer interface technologies for human factors applications in cognitive training, system adaptation, and human autonomy teaming. So Dr. Pope's research has developed human response measurement technologies to assess the effects of advanced crew station concepts on the crew's ability to perform flight management tasks effectively. So thank you, Dr. Pope, for being with us, and I'll pass it over to you.
Thank you, Roxy. I'm going to be talking about our early work. This is kind of historical in nature. I'll be telling you about the foundations that we developed at NASA Langley, and Chad Stevens will tell you about the current work that's going on there. So psychophysiology and biofeedback was my background before I came to NASA, so I just brought that on board. And here are the two formal definitions of physiological computing and neuroergonomics. And I'll be describing work that was done at NASA Langley even before these two terms were coined. We were doing that kind of work without knowing the name of it. In 1980, as you all recall, I was recruited to NASA Langley to introduce physiological measurement into the flight simulator facility. I outlined a plan for doing this in an AIAA conference presentation in 1982. I think I used the term mental state in that presentation, in that publication. So this graphic from 1987 depicts an AI, an artificial intelligence, as the ghost figure monitoring the crew's psychophysiological state during flight. This is an ultimate goal, which is coming closer to being realized and has been with Chad and with John. One step towards developing a psychophysiological monitoring station, which I was tasked to do in the flight deck simulator, was recording the pilot's brainwave activity while they're flying the simulator. This is an older simulator, and they're carrying out flight tasks in this simulator. This is called the advanced cockpit simulator. It wouldn't be advanced anymore these days. The pilot wore a cap with electrodes, which picked up brainwave signals from many sites on the head and sent these to instrumentation, which then displayed the brainwave tracings and also converted them into color brain maps of the brain's electrical activity across the head. This is an open loop application as opposed to some closed loop applications that you'll see later, just monitoring what the pilot's brainwave activity was doing during their conduct of flight. And up until this time, the early 1990s, the focus had been on high workload or overload. But with the increase in automation on the flight deck, low workload was becoming a concern. So we examined the Aviation Safety Reporting System, ASRS, and identified instances of suboptimal psychological states that crew members reported themselves that contributed to accidents and incidents. So we determined to investigate what I termed hazardous states of awareness, or HSAs. The hazardous states of awareness concept resonated with Jack Hurst, the author of 2020 book, The Dangers of Automation in Airliners, who used the concept to analyze several notable airline accidents. This graphic is a visual depiction that I came up with of some of these hazardous states. Not all of those that we investigated, but this is intended to convey an intuitive understanding of the experiences. From the hazardous state of preoccupation at the top, with matters and issues outside the current context intruding on the thought, with thoughts appropriately active monitoring and focus monitoring in the two middle graphics, to a hazardous state of excessive absorption in just one aspect of the environment. So you see there are a number of ways to experience a hazardous state. So we turn to brain mapping with the technology that you saw earlier in the video to objectively identify these hazardous states of awareness. There are great individual differences in the power of discriminant analysis to differentiate these things. So that's one of the things we discovered, that individual differences was important. Since this was a complicated process involving multiple electrode sites and time-consuming analysis, we looked for other methods of discriminating measures to index these hazardous states of awareness. We were interested in kind of a duplex kind of interaction between the system and the operator, which we came to refer to as biocybernetic. So the important criteria was that the measure be derivable in near real time. The solution was an engagement index comprised of limited sites and limited brainwave processing. We compared the performance of several candidate brainwave indices and determined that of the ones we tested, the ratio of high-frequency brainwaves, beta waves, to the sum of two low-frequency brainwaves, alpha plus theta waves, performed best. And we realized that a closed-loop configuration could also be utilized as an index assessment method. So this engagement index resulted from our search to find a near real-time neurophysiological measure to use as the control variable in a closed-loop configuration. So this development resulted from my quest to find a real-time neurophysiological measure to use as this control variable. And this is sort of a depiction of what was in the paper, and I won't go into the details there. This graphic, kind of crude graphic from the 1980s, shows in slow motion the closed loop system that we envisioned. The brain waves, that squiggly line dropping from the subject's head, is processed by the brain mapper into the engagement index, which is then used to inform the feedback controller to set the level of automation of a desktop simulator known as the multi-attribute task battery, developed by Dr. Ray Comstock at NASA Langley. So that's the idea of an adaptive automation system that we implemented on the desktop simulator. This histogram from a 2022 paper shows how the usage of the EEG engagement index compares to multiple other candidate neurometrics of training progress. It was heartening to me to see that it stacks up well. It's been used quite a lot. Not as much as workload, of course, since that was a very popular measurement. So I realized that such a feedback loop was analogous to the feedback loop used in brainwave biofeedback or neurofeedback, which I had a little bit of experience with. So this is a little bit something different. So instead of a desktop simulator, we substituted a video game and introduced video game neurofeedback. And we successfully tested it in a study at Eastern Virginia Medical School for the treatment of ADHD. And Dr. Ole Paulson was the principal investigator on that. So in video game biofeedback, a brainwave signal is sent to the video game controller that determines the maximum speed that the player can achieve, kind of a governor on the speed. So operation of this technology is shown in this next video. And the animation, which you'll see in a few moments in this video, shows how the system works. And there's a lot going on in this automation, so it's hard to pick out anything. The goal is to encourage higher frequency brainwaves, which is indicated by the waveform at the top of the graphic. There it is. You'll notice that when the brainwaves are slow, the player's car slows down, and when they're fast, it speeds up. The wires light up in the animation to indicate that signals are being sent over them. So the incentive here is for the player in the study, these were youngsters, to produce brainwave activity that indicated engagement, that enabled them to practice being focused and engaged. Then we've gone on to develop other biofeedback technology, video game biofeedback technologies. And one of these we did with the Wii video game system. And we've added to that over the years. And these are called spin-offs because they originate from the core research, but are applied in non-aviation use cases. And we created bio and neurofeedback systems using signals detected by consumer grade and wearable physiological monitoring devices aimed at helping users to train self-regulation skills while they're playing video games and other recreational activities. These biofeedback technologies are similar to the closed-loop adaptive automation capabilities that you saw earlier that we developed in the core research. So I've touched on 3 areas of our early research. I've shown some of the seeds of physiological computing and neuroergonomics at NASA Langley. And those, of course, included brain mapping, the closed loop system for identifying that engagement index, and then the use of that closed loop concept in video game biofeedback. And we're still developing patents and patent applications in both the aviation area and the spin-off areas. These are from 2020 and 2022 and 2024, I think. Thank you very much.
Oh, and Roxy and John, I think you all are muted right now.
Sorry.
Sorry, go ahead.
There you
There
are.
is one of us.
I was
should
just
be.
talking into the air. Yeah, so for those in the audience, if you have any questions, feel free to post them in the chat from Dr. Pope's talk or from Dr. Munoz's talk earlier as well. But we will move on to our third and final speaker. So let me just pull up the intro here. So yes, Mr. Chad Stevens, aerospace technology researcher with NASA Langley Research Center in the Crew Systems and Aviation Operations branch, and he's been there since 2009. Mr. Stevens earned a BS in psychology and an MS in psychophysiology, and he has performed extensive research in the field of human factors with over 10 years of experience in the conduct of human subject research, experimental design, and aeronautics. So with that, take it away, Chad.
Thank you. Can you see my screen? Yes. Oh, wait, it's not showing the right thing then. Is it? Can you just see what the one slide? Okay. If I switch to this, yes. Okay. So I think this will work. There we go. Okay. Thank you so much. And I look forward to taking questions at the end. So thank you for that introduction. I'll just go to the next slide. So this is the overview for my talk today. I'll talk about where we fit in the structure of NASA, and then 2 examples of research we've conducted recently, and then very briefly the future directions that we have in mind. So new innovative technologies and operational concepts will be required to meet the ever-increasing global demands for air transportation. And the NASA System-Wide Safety Project, which is an aeronautics project at NASA, is focused on how future aviation advances can meet demand needs while maintaining today's ultra-safe system safety levels. The System-Wide Safety Project, or SWS project, is focused on evolving safety management systems as a means of achieving these safety goals. So what is a safety management system? We like to use the Federal Aviation Administration, or the FAA, definition of an SMS, which is the formal top-down organization-wide approach to managing safety risk and assuring the effectiveness of safety risk controls. It includes systematic procedures, practices, and policies for the management of safety risk. And I point that out because, as you'll see in the next couple of slides, the System-Wide Safety Project really is focused on developing the next evolution of the safety management system for commercial aviation operations, but also for emerging operations that are depicted on this slide. And then furthermore, you'll see even additional examples of vehicles that will be operating in the airspace. And so the System-Wide Safety Project is developing an in-time system-wide safety assurance method, and then also specifically an in-time aviation safety management system concept to enable the future operations, which will be increasingly complex and have inherently more risk in them. So as part of this effort, the concepts of resilience and productive safety are being studied by a team within the project, and we refer to ourselves as the Human Contributions to Safety team. And the HC2S team is really focused on making the most of your human and the capacity for safety producing behaviors that humans exhibit is not very well understood. And so that's why we are trying to apply traditional human factors methods, as well as developing new methods, including ML and AI, or machine learning and artificial intelligence capabilities, to accomplish risk assessment and risk mitigation capabilities that will enable the ISMS. So this is a diagram that we developed to represent a safety management system. It's very serial, and the risk mitigations are almost entirely reactive. That's not really going to be able to keep up with future demands, and it's not keeping up very well with the current demands as the system continues to become more complex. And so what we're trying to enable and develop is an ISMS with a very human-centric focus, looking at the human operators in the system and understanding them better and enabling them and leveraging their strengths. So the previous project that System-Wide Safety supported was focused on training for attention management. And that heavily incorporated multimodal psychophysiological methods to address factors identified as contributing to actual aviation incidents and accidents, and the development of training-based mitigations for those risks and threats. So this started in response to an analysis conducted by the Commercial Aviation Safety Team, or CAST, which is a large conglomerate of governmental and industry and academic partners who are focused on commercial aviation operations and maintaining and improving safety. A research group at Langley was working under the NASA System-Wide Safety Project, Technologies for Aircraft State Awareness Sub-Project, and we took the research plan that was developed by CAST to implement a safety enhancement focused on training for attention management. This focus on attention was due to the findings of the CAST analysis of loss of control in-flight accidents and incidents in which flight crews lost awareness of their airplane state, attributed in part to distraction in all of the accidents and incidents. So as you can see from this diagram, the only other category that contributed to all of these accidents and incidents was ineffective alerting. And another NASA team was actually focused on that safety enhancement. The NASA-led safety enhancement 211 training for attention management developed and implemented psychophysiological methods to detect attention-related human performance limiting states, or because we love our acronyms, we call them APPLES, including channelized attention, diverted attention, startle surprise, confirmation bias, and high workload. Additionally, these methods were validated in flight simulation context multiple times, and the research plan also included design and development of simulated training scenarios to induce the APPLES in commercial airline pilots. And the training focus of the safety enhancement involved developing and assessing training-based mitigations of these APPLES. So what our team built over the course of the first year, really, and then we further refined it in the subsequent 4 years, was an end-to-end psychophysiological monitoring system capable of assessing operator cognitive state in real time through machine learning analytics. And that's depicted in this diagram. So the system was designed to induce and detect cognitive states of interest and present a proposed mitigation capability for use in flight training context. The system involved a paradigm of benchmark tasks, which are depicted in the upper left-hand corner. And those were performed by the commercial airline pilots while their psychophysiological data was recorded. The psychophysiological data was then used to train machine learning algorithms to discriminate the 6 cognitive states with greater than 80% accuracy. And then the test subjects subsequently completed flight simulation scenarios that were also designed to induce the cognitive states of interest, and the classification algorithm then detected operator state based on the psychophysiological data in real time. So that's the detect part of our research plan. This is the induce part. So we also needed to create line-oriented simulation scenarios, much like what the airlines do every day and implement for their pilots' annual recurrent training, that had event-based approach to inducing these states. And so what we did was we designed these scenarios to provide high-fidelity simulation of line operations with event sets to induce the APPLES. The NASA Langley Research Center subject matter experts and line operational commercial airline pilots with more than 30 years of combined experience assisted in the design of the scenarios. And then the scenarios were also developed based on FAA Advisory Circular 12035D, which presents the guidelines for design, implementation, and validation of line-oriented flight training, or LOFT scenarios. Then we carried out this LOFT scenario, which included a gate-to-gate from pushback to taxi scenario with multiple event sets designed to induce APPLES. And I'll just call some of those out. So the very first event was a startle surprise event, a wake encounter after takeoff. The second event was channelized attention around a hydraulic system failure. The third was also a channelized attention event, trailing edge flap asymmetry, which we'll see in a video shortly. And then there was the final event was a runway incursion that occurred after they landed. And if you're familiar with airline training, this diagram may look very familiar because it is event based. We tried to design it very similar to that, and we had help from our major airline partners as well as Boeing. So the Langley team developed and assessed a training-based mitigation for apples that we refer to as the System for Human Attention Restoration Using Psychophysiology, or SHARP, instant replay tool. The intended purpose of this tool was for flight instructors in training facilities to observe psychophysiological data-informed assessment of pilot psychological state while performing flight simulation scenarios to induce apples. This novel tool was intended to add to the performance assessment and behavioral observation completed by flight instructors to enable feedback to pilots with regard to development and sharpening of attention management skills. So our end user was not actually the pilots. We determined by interacting with the airline partners that we have, as well as Boeing, that the flight instructors were actually the ones that were going to use this tool and would probably have the most effective application. So the SHARP Instant Replay tool consists of a mosaic video display, including an over-the-shoulder camera view of the flight crew in the center, an out-the-window view in the top center, avionic displays. Those are the displays that the pilot looks at when they're flying the aircraft, are depicted in the lower left. And then this image in the lower right is an animation of the flight control inputs made by the pilot. So they didn't actually see these, but it was helpful for understanding what inputs they were making to the aircraft to control it. The additional displays in the upper left and right are the psychophysiological data-informed assessment of pilot psychological state displays, and these are updated in real time by machine learning algorithms, classifying and indicating one of 6 possible cognitive states. So next I'll play a video that shows this system in operation while the professional commercial airline pilots were performing the loss scenario that we designed to induce apples. And this is actually a recording from our second simulation study that we conducted in the SHARP series. It shows the system working in real time as they're performing the scenario. So this is not a post hoc analysis. All the algorithms were working live and doing the classification in real time. So let's see here. Switch to the video. This will be a question of whether, let me know if the audio does not start.
All right, approaching gate is below 195. Gear down, flaps 20.
Gear down, flaps 20.
Trailing flap asymmetry.
Yeah.
Seriously?
Well, at this point, we're at 2,000.
Gears down. Below 190, flaps 25.
Flaps 25.
Below 162, flaps 30.
Flaps 30.
Approach is 127.
Not symmetrically extended. Do not arm the trailing edge. Alternate. Yeah. Okay. Do not indicate. Flap position at or greater than 20. Yes.
Yeah.
Re-ref 20. So add. Yeah. Did you add that?
Oh man. Okay, this is where we go. Hello up there. This is where we divert and go to another airport if we can't get a longer runway.
Okay. Because we're at 195. So now I bet we're gonna have an issue with the. Between 515 now.
Tell Memphis we'd like to climb back up to 3,000 feet.
Memphis Tower. We have a Ongoing problem, we're gonna have to go missed approach, runway heading to 3000, we need to divert.
Mass 557, Roger. You can climb and maintain 3000 fly runway heading and expect radar vectors shortly.
Okay, runway heading 3000, NASA 557. All right, so at this time, we'll probably send a quick message off the ACARS, let them know we're diverting.
Yeah, we'll clean up, get me out of approach mode first over there.
There you going.
Keep positive rate gear up.
Rate
Flaps fit 20.
It's 20, you're already in there. I'm gonna put you into climb. Put you in the go-around mode.
Now wait a minute, something,
There we go.
something ain't right here. There we go.
Gear's coming up. There you go.
I ain't gonna tell you how close we came to the ground just now.
I saw the lights, but
Yes.
Okay, so now I'm back to presenting the slides. So in that video, the flight crew had already completed about 2/3 of the loft scenario, which included a startle surprise event and channelized attention event. And when the video started, they were approximately 2,000 feet altitude, and they experienced another system issue, which was a trailing edge flap asymmetry, which they proceeded to address. We'd like to use that as one of our examples from the study because it presents the real-time psychophysiological data-informed assessment of the pilot's psychological state while they're experiencing apples induced by the scenario. Also, it was completely voluntary that the flight crew, both of them, verbalized the loss of airplane state awareness they experienced during the simulation. So that indicated to us that the scenario was efficacious, and then also the performance of the classification system was working quite well for this flight crew. We have some of the other examples from this study where only one of the flight crew experienced channelized attention, and the other flight crew member recognized that they were in that state and actually assisted them in getting out of that state. And they did that of their own volition. We didn't tell them that we were trying to induce these states, but some of the other crews exhibited some resilient behaviors like that. So the purpose of this system was, as I explained from the research plan, was to detect the states that were induced by the scenario using the psychophysiological methods. And both of these pilots were wearing EEG. The captain flying the aircraft in the left seat was also wearing FNIRS during the simulation, and then other autonomic measures as well as eye tracking was captured. So that's our best work in that area, and we've continued to develop the system, and we've published on it. So you may have detected, based on what Alan was talking about, the biocybernetic system and what John has been developing recently in that regard. That system that we built, the Sharp Instant Replay tool, was developed for use in commercial aviation training, but it didn't incorporate the neuroadaptive technologies. So the pilots weren't being directly informed about their state. Instead, the feedback was provided to the training, the flight instructor, and then the flight instructor would impart that feedback to the pilots during a debrief after the flight simulation session. That was intentional. We built the system that way so that the flight instructor would be able to present that information to them. We also intended not only for the system to detect problems like when the pilot got channelized or startled, but in interactions with the flight instructors, we indicated that it would be possible to help pilots if they did get have that experience, but then also if they were able to mitigate or do something resilient that guarded against channelized attention, the flight instructor would be able to detect that as well and say, hey, you did a great job. How did you do that? how did you recognize the situation that might lead to channelized attention, or how did you guard against that so that you can do it again, in the future? So we've written about, the controls aspects of this system as it was designed and published with some of our colleagues. And we continue to develop the system and try to license the technology to flight training system facilities as well, at airlines, as well as with OEMs. We have one patent. I think Alan mentioned a few of the other ones that have been licensed, and they've been licensed for the using commercial astronaut training, military and law enforcement training, but as well as virtual education and professional development. Also, we did publish this data set, a portion of this data set publicly through a data science competition. There's over 170 teams that accessed the data set and participated in the competition. And this data set is still available at this link here. I also recently learned that there have been about half a dozen publications using this data set as well. So that's really encouraging that it's continuing to be valuable. Next, I'm going to talk about NASA's human contributions to safety research under the System-Wide Safety Project. So too often when we think about the human element on the flight deck, we focus on human errors that happen rarely and ignore the everyday adjustments that flight crews make to keep operations safe. The human contributions to safety, as we call it at NASA, is intended to capture and describe what human flight crews routinely do right. Most of our learning about human performance in aviation comes from studying relatively rare errors and failures. And the lead for this project, Dr. John Holbrook, and the HC2S team started by considering information from an analysis of line operational safety audit, or LOSA data, which is part of a safety management system, which indicated that pilots intervened to manage aircraft malfunctions on 20% of normal flights. This is the ParkCast report from 2013. So if you combine those percentages in the context of the 10 years of worldwide jet data, as published by Boeing in 2017, you can generate this contingency table depicting outcomes, not accident or accident, by whether human intervention was identified as being associated with that outcome, and that's shown in this figure. The main takeaway is that humans are a significant source of successful system performance, and in fact contribute to safety far more than they reduce safety. Indeed, extrapolating from the data in this figure, we suggest that pilots intervene to keep flight safe over 157,000 times for every time that a pilot error contributes to an accident. So that's, you can't ignore that. So then we started to look at actual data. So from the HC2S perspective, building on resilience engineering literature, Mike Stewart, who's a member of the HC2S team, and others analyzed aircraft flight track data for more than 10 billion flights into 32 domestic airports, which revealed that only 12.4% of the flights fully complied with vertical and lateral profiles on published arrivals. So that means they were doing what they were supposed to do according to procedures, only 12% of the time. The insight gleaned from this was that human operators are producing safety more often than they would be expected, given these deviations from their required thresholds. So the human contributions to safety is definitely an alternative and complementary approach to traditional human error, or what's often referred to as safety one. And Dr. Holbrook and others further examined this by looking at safety producing behaviors during arrivals by collecting data from pilots, both mainline and regional airlines, and then also terminal radar approach controllers or air traffic controllers. The team conducted interviews to understand routine disturbances during arrivals into specifically Charlotte Douglas International Airport in North Carolina in the United States. And they reported that the different data sources resulted in different estimates of the frequency of non-adherence. So just the perceptions of the operators in the system are quite different. So these findings highlight how published procedures can be misaligned with routine and safe operations. The reasons for the misalignment interpretation of these findings cannot be addressed with traditional approaches to risk and safety management. So the alternative approach of looking at human contribution safety is called for here. So again, what we're trying to do is look at changing the definition of safety, not only to reflect avoiding things that go wrong, but also ensuring that things go right. And that's what system-wide safety continues to support the human contribution safety work. So in that regard, what the team tried to do was to systematically collect empirical data to explore the practical application of these concepts towards improving aviation safety and sustaining aviation safety. We designed and conducted the system-wide safety operations and technologies for enabling resilient in-time assurance, or SOTERIA, flight simulation study to create a data set to meet that need. And I'll note that our acronym SOTERIA was an intentional reference to the Greek mythological spirit of safety and salvation and preservation from harm. The SOTERIA data set enables identification and collection of data sources and indicators for in-time safety critical risks, examination of how to analyze those data to detect and prioritize risks, and specifications for how to optimize safety awareness and safety action decision support toward development of the IASMS for both traditional aviation and future aviation concepts of operation. So I'll present some preliminary results from this study, and I'll note that this study was conducted under approval from the NASA IRB, and all the subjects provided informed verbal and written consent to participate. So the methods included video and audio recording of flight simulation scenarios, as well as traditional human factors, measures of workload, situation awareness. We also developed a custom resilience questionnaire, which we called the Resilient Performance Self-Assessment, or PSA, that allowed for self-assessment of each pilot's performance. 16 questions were modeled on American Airlines Learning Improvement Team proficiencies, which is not yet part of their SMS, but it is contributing informally to the SMS at that airline. The participants were instructed to specify whether they made use of these particular behaviors, and if so, rate their perceived success of implementing that behavior. So these were self-report measures. We also incorporated an array of psychophysiological measures, including eye tracking, EEG, and autonomic measures with various devices. To integrate the data, we use an off-the-shelf capability that's provided by ICEDX. It's the multimodal analysis of psychophysiological and performance signals, or MAPS. And this allowed for data synchronization and aggregation, as well as triggering the recording with the flight simulation itself. Then we exported the data from MAPS and processed it with some custom Python scripts. We are still continuing to analyze the eye tracking data. So in these results, I'm just presenting a subset of the eye tracking data. The research questions that we have today to talk about these results are: do resilience scores differ by crew? And then do the same crews that exhibit different resilience scores exhibit differing psychophysiological behaviors, specifically in the eye tracking measures. To test our hypothesis, we used a linear mixed effects model, LME4 packaged with an R to perform linear mixed effects analysis. We fit multiple linear mixed models and ran a single model for each variable of interest. And we're presenting the results from the RPSA data. For RPSA, we treated each of the 16 questions as repeated measures, assuming equal weighting, and used fixed effects of crew and seat, left versus right, and subject as a random effect. And based on this, crews 6, 8, and 10, indicated in orange, showed the lowest RPSA scores, and were significantly different from crews 1, 2, 11, and 13. which are indicated in green. And this is with a 95% confidence interval that did not overlap. So based on that, we looked at the eye tracking data, and the eye tracking metrics consisted of varying total repeated measures by crew and scenarios, since we used the average across the 10-second epochs for each dependent variable. The models contained the same factor as the model for the RPSA, and we performed post hoc pairwise analyses for each model by calculating the least square means and estimating the 95% confidence interval using the R package EM means. The significant findings for crew 11 were their gaze variance score, but that didn't transfer to any of the other eye tracking metrics. So basically, this suggests that crew 11 looked at more of the cockpit than the other crews throughout the scenario. So that was one sort of outstanding indicator for that crew, which was one of the most highly resilient self-reported crews. For crew 8 was one of the crews that showed relatively lower resilient scores. They exhibited the lowest gaze velocity of all the crews, and that indicates less shifting of attention over time. And so based on this, we're thinking that gaze velocity might be a candidate for predicting resilient behavior. And then also crew 8 had the largest pupil diameter of all the crews, and pupil diameter has been correlated with demands on sustained attention. So we think that might be a candidate for predicting resilient behavior. So based on these results, we were able to assess the crews and discriminate them, and then also find some examples in the eye tracking data by itself that could be used for resilient indicators. So there are some considerations that we've discussed with this preliminary analysis, and we plan to address those in future analyses of this data set. We do have one publication that was presented last year that talks about these initial results, and we are currently in the process of very close to having approval to make this Soteria data set publicly accessible. And the way that we're doing that is making the repository on a NASA approved service, and then also publishing a paper in Nature Scientific Data Journal, which is a data journal to enable public access. So our future directions include supporting the development of the concept of learning from all operations. So this is the current title for that industry and other government organizations are using for resilient performance in flight operations. It's highly similar to the human contributions to safety philosophy. So if you see learning from all operations, that's in the same regard as human contributions to safety in the literature and in industry. We're actively collaborating through NASA Space Act agreements with major airline partners, as well as OEMs. And then we are engaging with multiple licensees of the NASA technologies through the NASA Technology Transfer Program. And that is really the best way that we can get the technologies to be made available for use in industry. Of course, I have to thank all of the collaborators, and these are the research team members. There's a large number of team members who supported the work in the simulation services, as well as the research services areas of NASA that are not included in this list. This is just the research team, but I have to thank them for all of their hard work and continuing efforts in this research. And that's all I have. Thank you very much.
Thank you, Chad. Thank you so much. That's a lot of great work being done at the Langley Research Center. So yeah, we will open it up to questions now. So if anyone has any burning questions in the room, feel free to raise your hand. And we also have the chat function for folks who are online. I guess I can start us off and just, I really love the idea of the open access elements of these data sets and NASA is allowing the scientific community, and even, maybe citizen scientists or people who are just interested in aviation to take a look at these data sets. So, and we also have in the room and maybe online as well, lots of students, graduate students who may want to collect some of their own data using their own technologies. And I'm just curious if NASA has any, I guess, guidelines, best practices, standards, or anything like that that's been published or is in the works to be published in the future on how to collect data themselves so that we can have all of these data work together, if you know what I mean, so that, we can build a much larger data set, if that makes sense.
Right. So I know that NASA as a U.S. federal agency, we're trying to abide by the federal requirements for publicly funded research to be accessible. So that the results of that research and the data, including the data, there is a public access plan that NASA is developing. Trying to see if I can access it right now, but I might need to find that offline. But those are the guidelines that we're trying to follow in this process. So that might be specifically for NASA, that might be the best point of reference. And I think within NASA, the other teams that I've talked to about this, I mean, there are a lot of publicly accessible NASA data sets, especially satellite data, data that's basically about space is also publicly accessible. So we're just trying to add to that, from the human factors part of NASA. So I can try to track that down and then share that with you, Roxy and John, and then you can just distribute that if that would be helpful.
Yeah, that would be great. Yeah, thank you so much. Any questions? I see one in the room. Do you want to
ask it? I guess going through the presentation, it seems like a lot of the data you collected for psychological monitoring is based off of the pilot population, which is mostly men. Do you not think it might be a slippery slope to then make evaluations regarding psychological status on female pilots off of data you collected from men? And do you think that could possibly negatively impact women in the field when they get their pilot's license? And as well, if this data is available to airlines, their evaluations in the field itself.
Mm-hmm.
First, I repeat the question.
Did you catch that, Chad and Alan?
Yeah.
So I'll just repeat just the gist of it for those who may have not caught it, that a lot of these data are collected from data sets that are mostly men. Is that right? And so how can we incorporate women into that psychological assessments, right, from these largely male data sets? Did I get that correctly?
Yeah, and I guess do you see this negatively penalizing women?
Yeah, and could it negatively impact women who are in the aviation field?
Right. So specifically within Soteria, we worked with our recruiter to bring in the women that participated, and that was a very challenging effort. We actually engaged with airline partners and talked to chief pilots at the major hubs to recruit more women into the study. So one of the chief pilots for American, she's a woman, and she basically engaged that whole network and brought us the pilots. The percentage of pilots, women pilots, is in the single digits for the major airlines. We actually were in the double digits for the number of women that were represented in our study. So we tried to address that. We have not looked at, in our data set, we have not looked at sex differences. That might be challenging with only having 24 test subjects in our data set. But it is a good question. We tried our best. In another study that we conducted at NASA, we tried to that study consisted of 57 pilots that participated, and we were only able to recruit 7 women for that study. So again, it's challenging because there are less women in the industry to recruit them. And then how do you look at sex differences in the data when we have these small sample sizes? So it's a hard problem, and we are cognizant of it, and we're trying to sample as best as we can. But I think it's going to take even more effort than we've been able to do so far. But thank you for that question. That's a good question.
So I'm just going to move to that. We did get a question from the chat, so I'll go to this one, and then I'll come back to you. So Shahab is asking online, very insightful session. Thank you. Looking at the near future, is there intellectual value in studying aircraft maintenance personnel in a similar scope as you have with pilots? Human-machine engagement and safety hold parallels.
I don't want to be the only one talking, but I'll answer first, I guess. Yes. So maintenance is a major part of the safety management system for commercial aviation operations. They contribute a substantial amount of data, safety data, to the SMS. And I know that our major airline partners are using technologies to try to assess the maintenance personnel and understand their behaviors better. And that includes not necessarily physiological monitoring, but they are, in a limited sense, trying some eye tracking capabilities in the training context. They're also trying to test VR, AR capabilities in maintenance operations. And then they're trying to take the data that comes from the mobile devices that the maintenance personnel are using when they complete procedures, and because it's large volumes of data, use machine learning machine learning based analyses on that data. There's a paper that I was the first author on last year that I presented at the International Symposium on Aviation Psychology, and we cited one of the very few publicly accessible examples of that kind of approach to analyzing maintenance data, maintenance personnel relevant data. So that paper is our paper, cites that presentation that the American Airlines partner presented. But again, it's a little bit challenging in industry because they're these methods they're trying to develop for efficiencies, but then also for safety. They tend to be more sharing about the safety aspects between the various airlines. But there's still a little bit of difficulty, transferring between airlines because they have different procedures and things like that. So very good point about maintenance, though. I think there's a wealth of information there that could be further leveraged for benefit to safety, and then also sustainability of operations.
John or Alan, anything to add to that? I know you, well, John, you've worked with other applications. So on the same vein, right, of thinking beyond just pilots, John, I don't know if you want to speak to the work you've been doing with even just police officers as well.
Yeah, I think you mentioned, Chad, some of the other applications of this technology overall looking into military law enforcement. And that's certainly something that we have been able to spun off from the work that you have been doing in NASA Langley and taking all the methods and many of the learnings and some of the information of the patents and being able to use that to monitor the stress management of police officers when they're going on their scenario-based training, and in particular using virtual reality for that. And certainly we have noticed how the police departments have been really open to explore those metrics because they normally don't have access to it. But they have the theory, and theoretically they always explain the importance of self-regulation, breathing, and all the fight and flight and rest and digest responses, and the importance of regulating those when you are on a certain situation that requires, for instance, de-escalation skills. So there's plenty of value that we always notice every time we go and talk to those participants.
Yeah, so lots of applications beyond just pilots. You want to ask your question next?
Yeah. I'm wondering, like, if there is a way to know the stress level of these pilots before and after using this attention management system. And also, it looks like the stress level assessment is coming from EEG data expression. And I'm wondering if, like, using cortisol, like, monitoring, which biomarker is the main stress level hormone, will be more direct compared to EEG-based type of measurements.
Okay, so just to recap, is it possible to measure the stress levels before and after running them through these scenarios? And then also, what are your thoughts on the use of cortisol as a biomarker comparing to, let's say, what you would get from EEG? Who wants to take the question?
Yeah, it's a good question. So I'm aware that there are publications in literature that detail the physio measures, that have been most useful for assessing stress in human operators. And those are, single sensor assessments, but then multimodal sensor assessments. I think the system that we developed and the paradigm that we used of having benchmark tasks to induce the state of interest and then building a model for that individual of that state, let's say stress, so that you can then try to characterize that state in their job task execution in a simulated scenario or in a real job task. I think it could be successful. So I think this paradigm is well suited to this type of continuous data, and then also to the the machine learning based approach to analyzing the data. And then I'm somewhat aware of, with regard to stress, I'm not sure if you've said or referred to measuring cortisol as a method. I know that in my department in graduate school, there were faculty and students using that method and in combination with psychophysiological measures as well. And they did have success in connecting those type of long-term measures like cortisol levels with the more instantaneous continuous measures from psychophysiological measures. So those are the things that I'm familiar with, and I feel like that there would be some success there.
I think just to complement that also in terms of the pre and post for all of these experiments is very we often use baseline recordings. So normally 3 minutes is just kind of like too short. 5 minutes is it's better. 10 minutes would be probably very ideal for many of these baseline recordings. So what you do is before starting everything, gathering with all the same physiological sensors, you have a baseline state of the participants, and then being able to compare that baseline against the responses that they're having during the scenario is normally a good way of exploring the elicitation of those physiological responses during the training. So yeah, probably Chad didn't mention that through the whole experiment, but I'm pretty sure in most of the cases they use any kind of baseline recording.
We
Yeah.
are kind of out of time.
Sorry, yeah, we have a last question, I believe.
One more question. Okay.
Sure. So one of the lines I caught on was the automation failure in airlines, where initially there was too much workload, now there's too little. And I know speaking to some of the pilots, it might be wrong, but initially 15 years ago, they used to say that AI does the control of the airplane when the weather's nice. But recently, when I talked to some of the pilots, they're saying, well, AI takes care of the more difficult stuff now. So what has happened is before I used to be worried when there was thunderstorm outside, but now when it's nice and sunny, then I'm petrified because now I know the pilot has the option of manual control. But what I'm trying to draw the parallel with clinical as well. So that's happening in clinical too. We're seeing more and more automation outperforming humans. So, and then going back to the fact that humans are still part of the system and we're training them using simulations that are not up to par with real life situations. So what are we doing to tackle this? Are we expecting that the simulations will get as good as real life in the near future? Or is there something else that's happening to make sure that the human that you mentioned is part of the system and you're trying to make the most of your human? What is being done to ensure that moving forward, humans who are a big part of the safety and a part of the system, what are we doing to ensure that the humans remain an important and valuable component and not just become a liability in the system? Sorry about the really long question.
Yeah, essentially, how do we keep the human in the loop is the question.
I guess I have my opinion on it. And I think it's aligned with the human contributions to safety work. So first, recognizing that the human is a source of safety is important. And then that informs the use of automation or autonomous capabilities in the system. Let's say it's the commercial aviation system or the national airspace system. You have to decide if implementing that automation is going to interfere with the safety producing behaviors that the humans bring to the system. And so that's in the policies, and applying the existing technologies, and then taking a step back and at the design phase of technologies, not just making the assumption that if you remove the human, you remove the error associated with those humans, because that's not a valid assumption. It just reveals that you don't understand or appreciate the value that the human brings to the situation. So you have to make sure that in the design phase, the human is carefully considered and their contribution is carefully considered. And then you also don't design automation or autonomous capabilities that limit the ability of the human to produce safety. So that's another kind of nuanced part of design, is that you're not in the effort to reduce or eliminate errors produced by humans, you're not limiting them from being able to save the day when necessary. And it's not even just saving the day. It's sort of the expertise that they bring about the overall system behavior that allow it to be as safe as it is, with all of the limitations and constraints that are in the system already. So I think that's, the design is really important. There's a lot of design considerations, and then the implementation is also very important. Yeah, I'll stop there. Thanks.
Yeah, also just my opinion, but training itself is designed to make pilots more useful in flight operations. And of course, automation is usually ever vigilant, more so than humans. But if we can train contingent management, which is one of our objectives, then humans can challenge the status of automation with regard to vigilance and attention.
I would say that overall in the design process is when it comes to creating these agents and this intelligence, it's always good to involve and include the stakeholders, in this particular case, instructors for the flight instructors, and when you work with the law enforcement, would be the police instructors when designing those tools, because that will certainly ensure that you're covering certain elements that are relevant and important from their perspective, rather than from your own technical scientific background, which brings a lot of biases. So that's from a human-centered design perspective, always involving that perspective helps to bring more, I would say, capable and intelligent system, as opposed to systems that are only focused on the accuracy of the automation, as opposed as the utility or the how meaningful the automation can be.
Right. Thank you very much. I think that's a great place to end it. And now we have a brief demo of the flight simulator downstairs. So thank you everyone online for joining this session. It's been really, really insightful. I've really enjoyed the conversation. And look out for some future events. Maybe we will have some more if there's lots of interest on this topic. So thanks again to Chad and Alan. Thank you so much for your presentations. Very, very cool. And we'll see you again soon.
Thank you.
Bye.
Thank you, Chad. Thank you all for attending. Bye-bye.